Okay, so let's get started. So for this session, we start with looking at the syllabus and then explain a little bit to you what this particular course is about, and then we probably take some time to introduce ourselves briefly. I know I see some names that we have been in a previous class for 605. Glad to see you guys here again, and and then we can briefly we can spend some time on the first two chapters too, because they would have two homeworks due by the end of the week. I know that some of you probably um, have already submitted the first homework. That's okay. Hold on. Okay, so we actually let's go through this very briefly so that you can get a sense on what the course is about, and then we can continue with the syllabus. I actually have an introduction video there in the first week, I think. If you didn't get a chance to um, to review, you probably want to take a quick peek there. It's around 15 minutes. Hopefully, it doesn't spend waste you too much time. waste you too much time. So first of all, what is mathematical modeling, and what type of problems that we're trying to solve here, and we can get ready for the course. And this is my contact information. In case you have any questions, send me an email or give me a call if needed. And then, so you're encouraged to send me an email or ask me from as the instructor section, even though it's very difficult for me to check that section during daytime. So I'll try to take a look every day if possible. And then, what is math modeling? A math model, essentially, a math model is a description of a system using mathematical concepts and language. The process of developing a mathematical model is termed mathematical modeling. So a model may help you to explain a system, study the effects of different components, and make predictions about behavior. And then let's look at what's the major applications. So it can be used in physics, biology, earth science, meteorology, economics, psychology, even sociology and political science. So it really have a wide range of applications. And then math modeling itself can take multiple forms. It can be dynamical systems, statistical models, differential equations, game theory models, and also something specific called math programming. And then it includes linear programming, nonlinear programming, and integer programming, even heuristic programming as well. But this mathematical programming itself is not really programming, IT technology programming or development. It is just a branch of applied mathematics, and then linear programming and all this nonlinear and integer are all optimization problems. So from the problem itself, it can be linear, can be nonlinear, can be static or versus dynamic. It can be explicit or implicit. It can be discrete or continuous. It can be deterministic or probabilistic, and the deductive, inductive versus floating. And then we're going to go through this in much more detail in our models, in our later on all the lectures. And then so essentially we have, if you look at this, we have real-world data. We are trying to use a model to simplify the data. As you can imagine, in this simplification process, we could embed some sort of assumptions in the model, meaning that some of the less important factors we probably will be dropped. That way we can simplify the problem so that really a mathematical model can represent the real world data. And then we do some analysis, make some mathematical conclusions. We're trying to use these mathematical conclusions to do some interpretation, to do prediction and explanations. And again, after we have some type of predictions, we use real data to verify our predictions so that we are sure that the model is a solid one. That's the whole idea of math modeling here, the whole process. So I think it's very important that, as you can imagine, for one problem, different people probably can come up with different model to model the same problem. So in other words, the modeling form can be drastically different. Hopefully, the model results is one way to judge whether the model itself is sufficient or whether the model itself is a good model. So in reality, I want to let you know is it's not a matter of right or wrong. It's really the thought process that's embedded in the modeling process is very important. Okay, so we can see that, for example, one of the real-world problems that we can solve would be we call it the TSP problem, which is also traveling salesman problem. So suppose that a UPS guy, he needs to make a decision on which route he needs to take on a specific day. For example, he needs to start from UPS, goes to A, and goes to B, and come back to UPS. And then we know that we need to visit those two locations, A and B. This is a simple problem, right? If we, in this particular case, it's simple just because it only has two nodes to visit. Suppose that you have more than two nodes. It's really a complicated problem to solve from mathematics point of view. So let's take a look at this two-node problem. Three nodes if we think about the origin and destination of the UPS as well. And then if we use the traveling cost between different nodes, suppose that if you go to A, these 3 minutes would be the traveling cost from UPS to A. But on the other end, because of the traffic or something from A to UPS, it costs 10 minutes. So in this particular case, we can see apparently if we go to A first and then go to B and come back to UPS, it's less time. In other perspective, it's more efficient, right? So you don't really want to go to UPS, go to B, and go to A and come back. That would be the cost would be 19 minutes versus this cost will be 12 minutes. So that's one type of problem that we're trying to solve. But the reality is this particular problem is a mathematical problem. It's an optimization problem, nonlinear optimization problem that actually can be solved. And then in Wikipedia there's a page. Let's quickly go there and visit. Hopefully that won't take too long. So the idea is the same as I just mentioned there, right? We're trying to visit all the points with the least cost. That's the problem itself. And then here there's a toy problem for this one. But overall, this is a math optimization problem. It's saying that minimize certain costs with this type of constraints, which is almost saying that you have to go to a specific point and also you only go to that point once. And then this is saying that going out of that point, you need to just need to do that once. And then this is trying to avoid sub-cycles. So that is the idea for the math programming, even though this is really advanced formulation in math modeling. So don't be intimidated by this particular problem itself. So give you some idea here. So doing some computation to figure out where is the optimal route. This is another way that you can look at it. And then this is current optimum distance is 249. Hopefully, we continue to improve the objective function, which is we're trying to minimize that total cost. In any case, that's just an example to give you some idea about what is a TSP problem. And then there are some other problems, and including linear programming, shortest path. It's also good to look at this shortest path. So it's saying that if someone wants to go from O to T, which route he should be taking. That's the idea here. If we start this, the problem is a linear programming problem, and then we are using Dijkstra's algorithm for the shortest path problem. So and then essentially we use some sort of method to label the solved node versus unsolved node. We're going to go through this detailed example later on in our class. But here, just to give you a sense how this can be solved. Even though at this stage it takes a little bit shorter for ABC, apparently we got the minimum cost, which is A. So we already selected A, and then go from there to calculate all the distance that's neighboring this particular node, and then find the shortest from there. That's the whole idea here, even though it takes a little bit longer to solve. But this is one of the problems that we are going to talk about in this course. And then linear programming itself, let's quickly take a look too. So linear programming, we always, for math programming, we always have an objective function, and then with certain constraints. Let's ignore this non-negativity for the time being. So, and then essentially, suppose that we know that we have limited resources. We have only $4, for example. And then we know that if I buy one set of X1, I can get 15 happiness of index of 15. And then on the other end, if I buy 1 unit of X2, I can have my happiness of index increase by 10 points. That's why we are trying to maximize this particular function, which is 15x1 plus x10 times x2. But because I have a budget constraint, I said, okay, x1 plus x2 has to be less than 4 units. I cannot buy more than 4 units. And then on the other end, I cannot buy more than 2 units of x1, which may be just because x1 is too sweet, it's not good for my health, and then I decided, okay, x1 has to be less than or equal to 2. And maybe some other reason we say, okay, x2 has to be less than or equal to 3. This is basically a classic linear programming problem. And then on the other end, I say, okay, I cannot get a negative x1 or negative x2, so I have a constraint of x1 larger than 0, larger than or equal to 0, and x2 larger than or equal to 0. So I'm sure that it looks fine so far, right? And then if you continue with this, you would find that it's all mathematically, it's not that hard, because we know that x1 plus x2 itself is a constraint, right? We say, okay, x1 plus x2 less than or equal to 4, meaning it has to be in this range. Anything that, if we want to satisfy this constraint, it has to be anywhere here. And then on the other hand, x1 has to be less than or equal to 2, so anything has to happen there. That's why this area in addition to that, x2 has to be less than or equal to 3. Then that's why this side would be the one that would be feasible. On the other end, anything has to be larger than or equal to 0, so that this is really my feasible region. This is called feasible region. On top of that, objective function is 15x1 plus 10x2. 15x1 plus 10x2 itself is just this line, right? Because meaning when x1 is 0, when x1 is 1, x2 is 0, then objective function is 15, which is all the way there. So essentially, but that's the idea. And then we have this objective function. Where is the optimal solution for this particular problem? We found that objective value is 50 when we x equal to 1 and y equal to when x1 equal to 2 and x2 equal to 2 as well. In that case, the objective function is 50, and then we know x1 less than or equal to 2 is satisfied, x2 less than or equal to 3 is satisfied, and both of them are non-negative, and the budget constraint is satisfied as well. Meanwhile, the maximum value is found, which is 50 in this case. It's just a nutshell for linear programming to give you a sense. And also, PageRank problem itself is a mathematical problem. Let's quickly go through that. The whole idea of PageRank is we're actually going through this example in class in more detailed fashion. The whole idea is that this particular node B has a lot of connections, meaning that you always click some page, goes to B, and then, of course, after you click B, it's possible you click some other page, then that goes to C. Then, because of the traction of B, we can use algorithm to find out that B itself is an important page. And then this is designed by Google's founder, Larry Page. That's why it's called a PageRank problem. It's really a network problem. It's a mathematical programming problem. Okay. And then, okay, with that said, very interesting application of network problem 2 is social network analysis. So suppose that we can we can model each individual person as a node, and then connection between people would be the link. In the network nomenclature, we call that as edge. So that, as you can imagine, that every person could have multiple connections, but we put all of them into a graph. In this particular graph, apparently we saw there are some cohesive groups of people. They're talking. They're well connected. That's number one observation. And then we can also study if on Facebook or on LinkedIn or on Twitter, let's study what this group of people are talking about. What's their keywords? And then we kind of have a semantic network to understand, oh, this group of person is really more interested in fashion. The other group of person are more interested in finance. Another group of person are more interested in politics. That's the whole idea of using network analysis, graph theory to understand social network analysis. And the graph theory itself is a math programming problem. To be more specific, it is a linear programming or nonlinear programming problem itself. Very similar idea here. Even though in social science there are some specific terms that we can study, such as this homophily and also even network closure, centrality, bridge. That's the idea. And then we can find the important person. narrative network of U.S. election 2012. That's the idea here, how to apply a math model to a social network analysis problem. Okay, without further ado, okay. Yeah, one thing that I have to let you know, it is really intensive mathematics, and then you have to follow my notes and the textbook very closely and ask questions if you have as early as possible and enjoying the course. One thing I really have to warn you that is for 605, if you have spent 3 hours a week, this course you probably have to spend at least, if not 3 times, at least 2 times of the effort for 609, because the course itself is just more complicated. And also, it's very important that you can get the textbook, even though I understand that this is not the textbook, but a textbook is not here. It's important that you can get the textbook, this one. Yes, I know. Some of you actually mentioned. I just checked the email. I realized that you sent me an email asking where we can look at sources for textbook. One of the possibility would be the page called half.com. Even though not sure if it's cheaper than Amazon, but hopefully it is. Even though it's more expensive, even though it's expensive on Amazon, you should consider either rent or get a Kindle version, or buy a new one and later you can sell it on Amazon. Even for used ones, you can sell it with a good price. So it's really up to you where you can get that textbook, but it's definitely important for you to get it because it's a lot of readings that you have to do by yourself on the textbook itself. Okay, so do you have any questions so far? If not, we can continue with the lecture notes, with the syllabus. No questions?
Yeah.
Okay, so let's continue with the syllabus.
Can you hear me?
So as you know, this is a core course, and then I don't really want to spend a lot of time on the course description, but the idea is it would include different system of differential equations, linear and nonlinear programming, algorithm search method for optimization, integer programming, branch and bound is one of the methods in integer programming, and then use of modeling packages in R. Again, you can use R optimization packages here. And then regarding the homework submission, you can use R to generate PDF, or if you prefer, even if you write in hand and take a picture, that's fine too. Even or you write in hand and then scan to PDF, that's fine too. But remember, just submit one file. If you have, for example, you have 3 homework problems for this week, and then you took 3 pictures, try to put them together as one file and submit. Otherwise, it's very difficult for me to keep track of all the submissions of different pieces of submissions. That's the only requirement. And then we're going to learn linear programming models and theory, and then we're trying to understand and apply branch and bound techniques for integer programming. We are going to learn quadratic and nonlinear program models. Remember that in machine learning, many of the algorithms itself is a mathematical programming problem. For example, support vector machine, which is called SVM, is a quadratic programming problem. When you're really learning machine learning, you probably don't need to know the math formulation of the problem itself, because you're going to really apply those methods using some sort of program or computer to understand how it works and understand the results of those algorithms. But fundamentally, you should at least understand what the problem is and you should at least understand if there's a formulation, you could read the formulation. You can understand um, what the formulation is about. And then on this regard, assignment and grading, first of all, we don't have a final exam for this particular course. We have three major things. One is the participation, and then I assign 14% to the online discussion forums and communication with fellow students. And then if you read the notes, I hope that you can submit one substantial discussion in that week to express your ideas. Those discussion topics are more related to, could be related to that week's material, but it's really on a very general perspective to understand if you are interested in, or to understand your understanding of the discussion topic itself. So that's that. For assignments, it's 14 assignments, meaning almost each week you have an assignment. And even though in the assignment list, I probably have more than 3. Majority of time I have 5 to 6. You only need to finish 3 selected problems of your own on the assigned list. Of course, if you are interested doing more, I'm open to assign, give more bonus points, even though that has not been thought through. If you do 2 more, how much points I should be giving you, etc. I would assume that if you do all extra 3, I probably can give you somewhere between 20 to 30% more points. Even though I haven't decided on that yet, I'll give you a head up on that part. And then there's one course project. This project can be team of 2. It is worth 30 points. There's detailed requirements on how you can get those 30 points. Basic idea is we want to get a draft proposal by August 25th, and then one final project proposal by week 11, which is November 8th. And then we have project presentation slides and actual project presentation. You can also write a final report. But final report, I don't really want it to be very lengthy. If you can give me anything less than 10 to 15 pages. I think I was saying like 10 pages. Let me check. I didn't specify, but it's really just explain the problem well and trying to analysis of the problem, methodology you used, details of the methodology and the findings of the project. Are they different from your initial expectation? If this is there any suitable explanation? I think if you can write that report within 5 to 10 pages, it would be nice. Of course, if you want to write more, you are welcome to, as long as you don't stress yourself too much on that front. And then that's that, 14% plus 56 plus 70. That's what our 100%. So we don't have a midterm exam or final exam on this course. And then you are going to use R. I hope by this point you already know how to use R for sure. And there is a supplemental material that you can take a look when you get a chance. And this is the required text and materials. Again, if you haven't got your textbook, you should start doing that right away after this, because otherwise you will have a really difficult time to finish homeworks. Okay, so try to do that as soon as you can. This is my contact information again, and then these are the detailed list of the topics and topics for each week. Okay, And then for now, for week 1 and week 2, both of the homeworks are due by end of this week. That's because I want to give you guys a little bit leeway for the first week. Otherwise, you just get in and then you have have a homework due in 3 days. That doesn't make sense. So this is the list. So read through the syllabus to understand a little bit more about the syllabus, and then let me know if you have any questions. I'm not going to go through the rest of the week's materials, but there is a last column to do and also readings that you need to finish for that week. We kind of followed the first required textbook majority of the time, even though a little bit later I switched to the supplementary textbook just because the required textbook doesn't have this concept of doesn't have this topic of integer programming. And that's that. Of course, some of the ethics and rules by the school you have to abide by, including academic integrity and some other issues that you may have. You may experience. Feel free to let me know if you have questions. Okay, and then in the syllabus, I also included this course project description, and then it has 3 options. You can go through it by yourself. One of them is basically to look at the problems in the textbook. The second one is any phenomenal or real-world problems, and then select one project with user method and 2 additional mathematical modeling methods. Compare those three methods if possible. That's option 3. Okay, and then any one of the 3 options would be valid. And then each team consists of 2 members. Of course, when it happens that we only, if you need 3 or 4, that can be accommodated as well. So don't worry about this requirement. Just let me know beforehand by the end of week 8. Let me know, okay, and I want to work with my friend X, or I want to work with my friend Y, and then we can form the team. And then we're going to have a project presentation and also the final project. That's the gist of the report that we also already discussed. That's the syllabus. So any questions on the syllabus or any questions for the course in general?
Hi, this is Shipra. I had a question. Like you said, I just wanted to confirm, are we supposed to do...
I have some questions that I missed. So, Sandeep Payan asked, what is integer programming? Okay, so the only difference between, let me, hold on. So as we said, this is a linear programming just because the objective function itself is linear, and also all the constraints are linear too. That's called linear programming. And then if we add a constraint, we see that x, y, and x2 can only be integers. Going back to my happiness index example, if I say that x1, x2 are all real things, maybe a chocolate or something, then it cannot be half, cannot be 0.3, cannot be 0.1. Then it's an integer problem. So in other words, instead of this type of feasible region, if we continue, instead of this region, the real feasible points will only be integers. Point here, 1 point there, 1 point there, 1 point there, so that instead of a region, it's really a lattice. That is called integer programming. Okay, Stacy mentioned that some people found a free PDF version. That's good, even though, okay, that's not sure if that's legitimate, but if you can find it, go ahead. And she rented from Barnes and Noble for the semester for 75. So that's a good option, I think. Up to you guys if you guys want to do that. That's for textbook. So Sanipaya was asking, can we extend the due date of submission for this week or for which one? Yes, you only need to finish 3 out of those 4 problems, even though this week we have 2 homeworks due. So, but the thing is, if we extended the deadline for this homework, next one will pile up. So let's do this. Please submit your homework by next Wednesday, which is the 9th, for homework 1 and 2. And then you can submit homework 3 on Sunday. I'm going to send you a announcement on this so that everyone is on the same page. Again, September the 9th by the end of the day, 11:59 Eastern Time. I'm trying to go through all your list that you have the question.
Thank you.
Yes, you can choose any of the 3 problems out of all the assigned problems. For homework 1, you need only to choose 3, and homework 2, you only need to choose 3. Okay, seems like you guys are having a lot of discussion on the textbook. That's a lot. So I'm still going through your comments here. Okay, for Nathan Nathan, yeah, I got it. So that's fine, no problem at all. No, you have to choose you have to work on 2 homeworks, but for homework 1, you only need to choose 3 problems. For homework 2, you only need to choose 3 problems too. Homework 1 is actually very easy. Okay, so pretty much I answered all your questions. Looks like we really don't have any time, but we still have a lot of things to cover. Let's continue for week 1. First of all, before you start, yes, 3 problems for every assignment. That's correct. Okay, continue with the week 1 material. So first of all, you need to review chapter 0, which is the review of integration techniques. Hopefully you know that already. If you don't, you should read them. Okay, read Appendix D, page APP-12 to get a sense on what the basic techniques that is needed. This is a prerequisite for this particular course, essentially. And then it includes U substitution, integration by parts, and rational functions, partial fractions. Hopefully, you have already studied this. This is, I think it's part of college calculus. So, first problem that we were trying to model in chapter 1 is modeling change. It's really easy in general. And then I discussed how to do the modeling, what's the intuition for the modeling. And then modeling change essentially is future value is a present value plus that change. Looks okay so far. And then, of course, when we have multiple stages, we can model each individual piece by delta A0 is A1 minus A0, delta A0 is A1 minus A0, delta A2 is A2 minus A1, so on and so forth. And then we can find that delta AN is AN plus 1 minus AN. And then graphically, we can see how this can be represented. And then there is a example in the textbook talk about how we can modeling changes with difference equations by understanding the mortgage problem. And then continue with this, how to model the change with difference equations, and then approximate the change. It's discrete versus continuous change. That's 2 types of problem there, and how to solve it numerically. That's the whole purpose of building a model. So observation versus prediction. If we really can do this well, it's not bad. Although if it's consistently lower, sometimes we would think that the model itself has under projection bias. We would try to figure out what's the problem there, why it happened. And then for dynamical problems, we try to look for pattern. We have a conjecture and try to test the conjecture, make some conclusion from there. Linear dynamical problems, AN plus 1 equal to R times AN. For R, any non-zero constant is AK equal to R powered by K times A0. This is really just you already studied some of this in high school even, I believe, right? How to model linear dynamical problems, also nonlinear problems. So let's say difference between linear is the relationship is really linear, but nonlinear apparently you have AN squared. AN plus 1 is a function of AN squared. That's nonlinear systems. And systems, there's very good examples of systems of difference equations on page 37 to page 52. So if you think you don't really have the time to read all the chapter, when it happens, definitely you should read the specific pages that I pointed out. You would be realized how much useful if you read the whole book at the end of the semester. You realize you would learn a lot. Otherwise, you probably feel like you learned something, but you are not sure for certain aspects. So that's why I really encourage you to spend time to read the textbook itself. Okay, here we have homework 1, we only need to choose 3. There is I don't try following your questions, you guys. Misprint of which page? Okay. Yeah, page 34. I'm sure probably a typo there on the textbook. Yes, I think so. I'm pretty much sure, but let me confirm and then I'll send another email. On page 34 on the homework, right? Okay, got it. I'll check and get back to you guys on this and send out an email. Yep. Okay, I'm going to check that. And then let's continue. Look at week 2. Week 2 is relatively speaking, it's very similar concepts of the first chapter as well. So don't read some of the examples there as well. So this is again real world problems versus mathematical problems. So real world systems really observe the behavior of phenomena, but mathematical world is a models mathematical operations and rules so that we can make mathematical conclusions based on the mathematical models. And if from real world perspective, we really use real world behavior to have real world conclusions. But on the other hand, mathematical models, we use real world expectations or predictions and use real world data to verify those conclusions. That's one way to look at this. And then from the nature of the model, it can be can be mathematical representation, can be replication of behavior, experimentation, and simulation would belong to this section, and mathematical model would belong to that section. And then there's a comparing of model types. Fidelity of real-world observations is apparently very high, but cost of real-world observations is high as well. On the other end, flexibility of real-world observations is not as good. But on the other end, some mathematical models can really do a good job on flexibility. Okay, so that's give you some perspective on why we need mathematical models to model real-world problems. And then all the steps: identify a problem, make assumptions, solve the model, verify the model, implement the model, and maintain the model. Itself is an iterative nature of model construction. In any of your current job or your future jobs, you try to build a model, you will go through all these processes and try to back and forth to improve the model. So it is iterative in nature. And iterative nature of the model construction, you have to simplify the model, you can refine the model, continue with the modeling process. This is an example of modeling using proportionality. It can be linear, can be nonlinear. And then in the textbook, there are some good examples. Hooke's law, Newton's law, Ohm's law, all these are proportionalities examples. And then in next chapter, we're going to learn how to fit a linear model. And then you probably already studied a little bit here and there for linear regression. But in this course, we'll have more detailed understanding of how you can derive that linear regression equation. And we can also model geometric similarity of the model. See here, chapter 2.4 and 2.5 have very good case studies on these topics. Definitely try to read those. And now we have homework 2. You only need to select 3 out of those 5, and then submit the homework. Okay, that's all for chapter 1 and chapter 2. Relatively speaking, it's straightforward. So finish your homework by September 9th, and we can continue. We'll see you 2 weeks from now. I don't know why the school said I don't really need to hold a session on September the 17th. So I'll have to send you an email if September 17th there will be a session, which I'm not positive at this moment. It could be some holiday or something. So, but I need to check on that front. If we have a session, that would be September 17th. If we don't have, next week I will have my no matter we have a session on September the 17th or not, I'm going to have my office hour next week, next Wednesday. Office hour happens to start at 8, and this course actually starts at 8:15. Just pay attention to those 2 times. And we actually plan to have an introduction of ourselves, but doesn't look like we have time to do that. So maybe we can leave it for next week, if next time when we meet, if time permits. Otherwise, we can skip that part as well, because we have this discussion forum going on already. That's pretty much what I have for this session. Do you have any questions? Again, takeaway for this lecture is you want to read the syllabus, you need to read the textbook, you need to be ready to spend more time than some other courses that you have taken in the past semesters. Without further ado, if you don't have any other questions, I'll stop here, and I'll stay for another 2 minutes. If you have any questions, go ahead.
Thank you.
Brett, so if you want to talk, you probably have to unmute yourself. Let me unmute you. Okay, thank you all.